And thank you for inviting me. I've been spoilt rotten already. I'm making a comprehensive tour of all the restaurants in the vicinity and learning about Korean food. Even had my first Korean lesson today, which was most appreciated. I met Youngjin in Eurocom in Pisa last year. And Youngjin came to Prague in January, and this week we'll be doing a little bit of work on the Tet polynomial, which I can't avoid mentioning in any talk that I give. I was a student of Dominic Welsh at Oxford University, and he was sort of very formative in developing the theory of the Tet polynomial and in matroid theory. And so this is an extract of a poster that we had at Eurocom with Jarek Neshatril and Delia Garijo, which doesn't actually make much sense, and it sort of reflects the state of unknowing that we had at that time about the topic about which I'm going to talk today. And to begin with, I'd like to just talk about the two objects that we're sort of bringing together, and they are graph polynomials and graph homomorphisms. So in order to introduce graph polynomials, I'm going to just talk about two typical examples of the great vast array of graph polynomials that are studied these days. And the chromatic polynomial, as you'll well know, was actually one of the first, well, the first to be formally introduced by Birkhoff in 1912, with a vague hope of attacking the four-color theorem by studying the properties of this polynomial. Could you deduce that this polynomial was non-zero when you set k equals 4 for planar graphs? And that, of course, wasn't quite how it worked out, but the combinatorial understanding that has resulted by studying the chromatic polynomial and its generalizations, in particular the Tet, have led to advances and connections between disparate areas of combinatorics such as knot theory and statistical physics, which sort of is to their mutual enlightenment. So the chromatic polynomial is usually defined as a counting function. You're looking at a graph and you're wanting to count the number of ways to color its vertices with k colors so that adjacent vertices get different colors. So that's what's meant by proper vertex k coloring. And when you define it in that way, it's not actually immediately obvious it's a polynomial. One way to see it is as follows, and that is just to rewrite proper colorings in terms of partitions of the vertex set of G into what are called independent subsets. So an independent subset of vertices is a set of vertices with the property that no two of them are joined by an edge. And these are the color classes. So these independent J different colors. And this notation, this is non-standard K falling factorial J. Don't worry about absorbing the information on these two slides. I'm talking about polynomials. This is just to give the flavor of the polynomials.
Do they ever consider dividing out by permutation of the colors?
Yes.
This divides out by that?
Yes. So you can think of so these partitions. They're not labeled.
Ah, I see. Okay.
So, but so we'll actually come back to this and we'll see the labeled version of it. And a famous theorem and typical of studying graph polynomials is we've defined it by evaluations. What are the coefficients? So we had the coefficients relative to this basis. So this is a basis for polynomials in K, but relative to the standard basis where you're looking at powers of K. These coefficients here are given by the Whitney broken cycle theorem, and they have a combinatorial interpretation. don't worry about what that interpretation. They have a good combinatorial meaning in terms of the graph. So this is typical movement. You define a polynomial, and then you look at other properties of the polynomial. What does it mean combinatorially? And so that was an early theorem of Whitney in 1932, which is now called the broken cycle or broken circuit theorem. So that's one starting example of polynomial. Another thing just to point out is that it satisfies what's called a deletion contraction identity. And this is like a recurrence formula, a reduction formula, so that you can compute it. It's not so much for computing it, because of course it takes exponential time if you're going to use this to calculate the polynomial in general. But it's very good for inductive proofs. So you can easily prove that this chromatic polynomial has alternating coefficients using this, and so on and so forth. And most graph polynomials have some such reduction formula to have a theory about them, because you can't really prove much otherwise. So a second example of a graph polynomial is the independence polynomial. And this is defined, instead of by evaluations, it's usual to define it by its coefficients. It's like a generating function for independent subsets of vertices of a given size. So for each, you count how many there are, and then you put the x to the j to label it. So it's a generating function. And so what sort of interesting things about polynomials do you want to look at? Well, here we also have a reduction formula. If you look at an independent subset of vertices, either V is not in the independent subset or it is in the subset. If it is in the subset, then you better make sure that none of its neighbours are in that. So you remove all its neighbours, and you've got the X because you're including V, but you have to remove all its neighbours. And so you have this basic recurrence. And actually this recurrence is quite useful. It was used to prove a result about the roots of the polynomial by Chudnovsky and Seymour in 2006. They showed that for a claw-free graph, a graph without K13 as an induced subgraph, this polynomial has real roots. And a very useful consequence of this property of having real roots is something due to Newton, and that is that you get this convexity of the coefficients. In particular, that the coefficients are unimodal. And a compatriot of most of the audience called Jun Hu proved actually quite recently that the chromatic polynomial has this property of coefficients, the absolute values. But that wasn't done by real roots. Of course, the chromatic polynomial has roots all over the place. So it wasn't quite so straightforward to get such a result for the chromatic. But in this instance, a combination of using this recurrence and it was a fairly elementary proof, but it illustrates how graph polynomials can give tangible graph theoretical results about combinatorial quantities. Right, so that's to give a flavour of what graph polynomials are about. If you're not familiar with them, don't worry, that was just to motivate why we like them. So the second thing we're looking at are what are called graph homomorphisms. And these are edge-preserving maps between two graphs. So if I have graphs G and H, I have a mapping from the vertex set of G to the vertex set of H. And I want the edges of G to be mapped to edges of H. It doesn't matter about non-edges, they can go to edges or non-edges. What matters is that an edge goes to an edge. And I'm interested in counting the number of homomorphisms from G to H. And sometimes these are called H colorings of G. We'll see why that is in a moment. So I'm interested in counting the number of homomorphisms from a graph G to H, which sometimes we look at graphs where the edges have some weights on. So there's a formal definition here. But for most of the talk, we'll be looking at simple graphs. So we're just counting ordinary homomorphisms. And so the problem or question that is animating all the following talk is that we're interested in sequences of graphs such that when you count number of homomorphisms from G to a term of that sequence, you get a polynomial function of the graph. The typical example, archetypal example, is that when I count homomorphisms to the complete graph on k vertices, I'm counting proper colorings of the graph, because an edge of G has to go to an edge of the complete graph, and they join distinct colors, and there's an edge between every pair of colors. And so we're actually looking for other sequences like complete graphs for which this is true. That you get a polynomial, an exact polynomial, for every value of k. And as I say, all the concepts come through simple graph sequences, but it is for the tap polynomial, as we're going to see, sometimes you need to see these multigraphs, but we'll be theoretically talking about simple graphs. And this is to indicate to me that I should pause for breath and just see if there's a general state of confusion in the audience, or whether any questions are required. Do stop me if something is not right. So here's an example. Oh, this is the example that I started with. If I take the complete graphs, counting homomorphisms from G to kk is giving the number of proper colorings. What about if I put a loop on each vertex, which I'm going to denote by putting a 1 in the air like that? So I put one loop on each vertex. In that case, a homomorphism from a G to one of these graphs has a complete free choice of where to send its vertices. It doesn't matter. And there's always an edge, so I'm okay. So k to the number of vertices. What about if I put L loops on each vertex? Now it gets a little bit more interesting. So if I am taking a function f from the vertices of G to the vertices of this graph, let's call them 1 up to k, then I get, for each time I map to a loop, I get L choices of where to put the edge. So if I have an edge that goes to one of these loops, there are L loops on that vertex. So I have L choices of loops. So for whenever I send an edge of G to the same vertex, so when it's monochrome essentially, so then I get a weight of L. In particular, if L is 0, this is back to the chromatic polynomial and forbidding monochrome edges. So if L is 0, this is exactly counting proper colorings. But in general, it's giving a specialization of what's called the Tut polynomial. The Tut polynomial is a generalization of the chromatic. It was Tut introduced it as a simultaneous generalization of the chromatic polynomial and the flow polynomial. It encapsulates duality between colorings and flows. And this guy here, if you're from a physics background, is the partition function for the k-state Potts model in disguise. This L is an interaction energy between states. That's a remark for the cognoscenti, not for if you don't.
Could you explain about the first example? I didn't understand.
This one.
Yeah.
Right. So when I have an edge, so here's G, an edge in G, and so I'm going to map. Let's do it to K3. I need to make sure that what's the property I need? I need that this is an edge, so I want FU, FV to be an edge in here. So what are the edges? 1, 2, 2, 3, 3, 1 in any order. And so this is precisely saying that I just want them to be different. I have a free choice as long as they're different. All I'm forbidding is going to the same. I can't send them to the same. I can't have FU equal to F of V. So this is then saying that f is going from the vertices of G to here it's to 1, 2, 3, and it has a property that for every edge, and this is saying that it's this is f is a proper 3 coloring. So this is if that makes it, yeah. So in essence, you're just because you have every combination you want, it just boils down to saying you're sending them to distinct colors. So think of the vertices as being the colors.
But a homomorphism is a map between vertex sets.
Yes.
From the vertex set to the other one. But when you're counting the different ones, you're counting which edge you're using when there are loops.
Okay, that's a very good point. So yes, when you have an edge, okay, I've not given a definition for homomorphism between multigraphs. So for between multigraphs, not only do an edge goes to an edge, but you can choose which edge you're sending to it, and then this is where, and they're counted differently. And this is precisely what is captured by this definition of hom. Yeah, it's as it happens, from after these examples onwards, we're just going to be looking at simple graphs. So it won't. But good point. Good point. And there is some leeway as to how you define that. So in this instance, this is why we have this. Yeah. Okay. Good. This example, homomorphisms to this sort of graph. Well. There's one vertex with a loop on it, and then I've got k independent vertices. So I've got a star k1, k, and then I've got a loop on the. Oh, that's not quite what that says. Ignore what that. So this is a star with a loop on its central vertex. And so what you're thinking about is, well, if I can send edges to this, the endpoints of an edge to this, safe enough, but I can't send endpoints of an edge to any of the vertices at the top. And so what you're getting is that if there's an edge joining two vertices, the only place I can put it is in here. But otherwise, if I have an independent set of vertices, I have a free choice amongst all these things at the top where to put them. So there are k vertices at the top, and if I have an independent set of vertices, I can freely choose which one of them to put there. So I've got k to the size of the independent set. And so remember the independence polynomial precisely had this x to the size of the independent set. So when you work out the number of homomorphisms when you're counting to these graphs, then you're getting an evaluation of the independence polynomial. And then a last example is to take the hypercubes. This box thing means the k-fold Cartesian product. And if I take this sequence, it's a bit more work. But it turns out that if you count homomorphisms, then you get a polynomial in k and 2 to the k. And this is a slightly different animal to what we're going to be talking about, but it will just feature a little bit later in some discussion later about some problems. I just wanted to highlight that you can get these bivariate polynomials in interesting ways for hypercubes. So hopefully that gives you a grasp of these sequences and what we're looking for. So we're looking for sequences of graphs for which the homomorphism count is a polynomial. This is a polynomial in two variables which are dependent, which, as I say, is going off in a slightly different direction to what we want.
But natural counter examples.
Sorry?
Are there natural counterexamples? Is there a natural sequence of graphs which is not a polynomial?
Yeah. Well, and in fact, cycles is one which we'll come on to, but that's if you most sequences are not a fixed polynomial. The property you want is that for every term in the every k, it's the same polynomial evaluation. Because otherwise you do get a polynomial, but it's sort of the choice. So it's key that this p of g is the same thing for every value of k. Otherwise, you can do it all the time. Because you count the homomorphism count is some polynomial, but it changes what it is. Yeah. So we're going to define this property. Of giving a polynomial as being strongly polynomial. The terminology comes from Delahaye and Gégé, a paper of 95. Right at the end, I'll show there are 3 papers on which this talk is based. But Delahaye and Gégé defined a sequence to be strongly polynomial if for every graph there is a fixed polynomial p of g such that the homomorphism count is an evaluation of that polynomial. And because of this basic property, you can always think, well, you need to check it for connected graphs.
So hypercube case is not a strong polynomial?
No, indeed. And so we've seen chromatic polynomial, the trivial k to the number of vertices. Actually, that one dropped out of my slides. I was weeding out lots. That gives a multiple of the chromatic polynomial. This one gave the Tut polynomial. So that was strongly polynomial in 2 variables. This is not strongly polynomial, but in these it is. So there is some work to do on. I mean, we'd like to study these sort of sequences as well. They seem to be interesting. And then I'm going to just describe a couple of non-examples, which are eventually settled down to a polynomial, but for small values make something different. And for me, and for proofs, in fact, it's good to translate counting homomorphisms to something perhaps a bit more familiar, which is to count the number of induced subgraphs of a given isomorphism type. And so what Delahaye and Gégé showed was that if I'm looking at a sequence of simple graphs and counting homomorphisms from G to HK, then I can partition these homomorphisms according to the image. Where do I send the vertices of G? So S is the subgraph of H, the induced subgraph of H, to which G is sent. And you're counting surjective homomorphisms. So this is vertex surjective homomorphisms from G onto the subgraph S. So that's just a simple partition of all the homomorphisms. And then if you're just interested in counting homomorphisms, you just need the isomorphism type of S. And so you go over all isomorphism types of subgraphs, and you're counting how many surjective homomorphisms you have and how many ways you can shift S around the graph HK. How many induced copies isomorphic to S do you have in the graph? And the useful thing about this is that it means that you and certainly for proving things, is that for each connected subgraph of H, you just want to check that the number of induced subgraphs isomorphic to S is a polynomial in K, a fixed polynomial in K. So we want this guy here to be a fixed polynomial in K. And so this is an equivalent condition. And if you're thinking about counting, how many triangles do I have? If I know the automorphism group of my graph, then I can, and I count the sides of the orbits. You want the sides of the orbits to be polynomials in K. So this is giving you the handle onto the problem. So for example, for the chromatic polynomial, you split it into well, you're going to map onto some subset of colors, so this Kj, and how many occurrences of Kj do you have in Kk? Well, you have K choose J, and this comes from the symmetry of the complete graph, essentially. So the orbit size of this isomorphism type of subgraph is k choose j. And so this explains why you get a polynomial. Just worth noting, this summation depends on k, and we want to get rid of that dependence on k. You want this to be for every value of k. And here, you don't like that here. But very convenient, well, the reason why you get a polynomial for every k is that k choose j vanishes when j is larger than k. So you can replace this thing just by the number of vertices of g. The terms that you don't want drop out because of that. And now to this example of cycles. So if you write down number of homomorphisms from cycles, either you're from G to a cycle, either using all the vertices or you're just going on to some subpath. The number of you can rotate the path round k times, so that's that here. And so what you find is that for small values of k you get something, and then it eventually settles down to a polynomial, namely the trivial one here, 0. It's constantly 0. So this is not strongly polynomial. Right. Whew. Okay. Now, so we've had examples of these sequences, and the approach I'm now going to describe is how to get from a given strongly polynomial sequence to a different one using some construction. And I'm going to give a sample of basic results just to give you a feel for how you can do that. So a combination of this paper, Delap and Gégé, and myself with Delia Garijo and Jarek Nesetril, you get such things as well. If you have strongly polynomial, then you can take the complements and it remains strongly polynomial. You can take the line graphs and it remains strongly polynomial. This sort of depends on the fact that apart from the small example line graphs are unique. If you know the line graph, you know the original graph, apart from the star k13, k4. And if you have if you take L disjoint copies of it, then you get something that's strongly polynomial. This is here just to turn back to this multigraph thing, just to persuade you that you don't really need to worry too much about these loops and things. So this is one result where if you have a strongly polynomial sequence of graphs where there's a loop perhaps on some of the vertices, if I remove all the loops, then it remains strongly polynomial. If I fill out all the vertices with a loop, it remains strongly polynomial. And if I add L loops, if I make sure every vertex has L loops, then this is strongly polynomial. So this was this tap polynomial example, essentially, just more general. So you can go from complete graphs to complete graphs with L loops by this result. So simple graphs are the things to concentrate on. The multigraphs sort of follow after. And so we had those unary operations, and some binary operations it's closed under disjoint unions and joins and direct products, lexicographic products. These are all graph products of one sort of another. Doesn't matter particularly if you're familiar with them. But just to illustrate the sort of thing we were trying to do in this paper, let's just try and build the examples we've seen, starting from something that is trivially strongly polynomial, the constant sequence, k1. So g to k1 is either 0 if it's got an edge, or it's 1 if it's an independent set of vertices. So it's a constant polynomial. So you start with that. And so you can take a multiple of it. You can take the complement then, you get the chromatic. You can add the loops, you get the tut. And then you do this join, and this gives something which generalizes the tut polynomial, which satisfies a three-term recurrence: deletion, contraction, and removal of the endpoints of an edge. And so we could build a lot of graph polynomials just by elementary operations from a trivial sequence. Not all of them. I'll mention some of them maybe if there are questions at the end, but for instance the interlaced polynomial is not among the ones that I'm not sure actually whether the interlace can be done by counting these homomorphisms. And so with Jarek and Delia, we were sort of happy with this, and we gave a more elaborate construction that involved representing graphs by rooted trees, like cographs are represented by co-trees, and we sort of made up some sort of basic toolkit of how to build strongly polynomial sequences. And yes, we had some things that were a little annoying. So for instance, we know that by joining these two we get a strongly polynomial sequence, these complete bipartite. And if we take the line graphs of these complete bipartite graphs, we get what's called the Rook's graph, which is the Cartesian product of these two things. And in general, we wanted to say, well, is it closed under Cartesian products, this property of being strongly polynomial? If I take any two strongly polynomial sequences and I take the Cartesian product, is it strongly polynomial? And what we were finding was that homomorphism counting doesn't really behave very well for Cartesian products, not like for the join or the direct products. You can't just write down what the number of homomorphisms from G to this graph is in terms of homomorphisms to this graph and this graph. And this is well known to be a difficult thing to do. So we were stuck. And then the other thing we were a little bit we wanted to reduce things to trivial sequences, and this is not a trivial sequence. This is a sequence of graphs called generalized Johnson graphs, where the vertices are subsets of 1 up to k of size L. So these are L subsets of this set. And you have an edge whenever the intersection of those two sets has a certain size. So you're specifying which sizes you like. So the Johnson graphs, as you defined, you want the intersection to be k minus 1, and the Knezzer graphs, you want the intersection to be empty. Maybe the Knezzer graphs are the most familiar. Like the Peterson graph is an example of a Knezzer graph on 5, where k equals 5, and you're looking at two subsets. And so a combination of results between this paper and our papers, you get the fact that this actually does give a graph polynomial. Counting homomorphisms from G to this sequence, you do get a graph polynomial. And we don't know much about this graph polynomial. It counts sort of colorings with restrictions on, so adjacent colors must be subsets for which, subsets of k for which this is true. Yeah? So it's like these restricted coloring problems, which are very well studied. But this doesn't seem to be. This counting colorings according to the Johnson graph scheme doesn't seem to be. And so we didn't think this was a basic building block, this sequence. It seemed to be special, it seemed to be something we should be able to build. And that was where we were when I gave my talk in Slovakia. And Patrice Osona de Mendes was in the audience, and I gave this talk, and this is where the story sort of changed a bit, and this is what I'd like to move on to. And it involves something which I'm rapidly learning about, which is model theory. And so Patrice and Jarek are looking at graph limits from a logic model theory approach. And they're using techniques which Patrice immediately saw were applicable to this problem. And I'd like to just try and pick out something which it's possible to convey in 10 minutes. It took me many months of trying to understand what's going on in here, so I've tried to choose carefully, because if you're not from a logic or model theory background, hold on tight. But let's just recap what we've done. If I have a simple graph sequence, I've said it's strongly polynomial if it has this property. The number of homomorphisms is a polynomial, a fixed polynomial. And then we saw this equivalence to counting induced subgraphs. So this is the number of subgraphs of HK isomorphic to F. So I count how many copies of F there are in HK. How many ways to embed f in HK. And this we wanted to be some fixed polynomial. Yeah, remember when we were looking at breaking down the homomorphisms into surjective homomorphisms. So this de L'Arpeggier criterion. So we saw this was the case. And then we had a set of operations that preserved the property of being strongly polynomial. We had complementation, line graphs, and we had various graph products, joins, lexicographic products, and direct products. And from these operations and trivial sequences, we could build a lot of interesting polynomial sequences, apart from the Johnson graph sequence. I haven't had time to mention the more elaborate. What I've described is a very small subset of. Well, it's a subset of the operations that there are. As I mentioned, more powerful operations involving representations of graphs by rooted trees. If you're familiar with tree depth and how you can encode a graph as a subgraph of the closure of a rooted tree, there's an operation on trees which is very natural, which is you have a subtree and you create k isomorphic copies of it. And this operation is producing lots of polynomial sequences. And that was more or less the content of the paper I've referred to with Delia and Jarek. Anyway, so we could get a lot, but we certainly couldn't get anywhere close to saying, are we getting everything? And so we couldn't even get this Johnson graph sequence. And we couldn't get the Cartesian product, which even more sort of, you feel you should be able to do that. And this is where this interpretation schemes approach that Patrice suggested really sort of with a scalpel knife cut through into that sort of problem. But I will say that there are many open problems which I'd like to have time to describe as well. Right. So I want to give a broad brush idea of how this works. It's an analog of these operations that transform one graph sequence into another graph sequence. The only change is that instead of starting from a sequence of graphs that we know to be strongly polynomial, we're starting with a sequence of relational structures which have this polynomial property. And that's what I'm going to try and define now. What it is for a relational structure to be strongly polynomial. Now, a relational structure includes things like a graph structure, which is given by a symmetric binary relation telling you whether two vertices are adjacent. But in general, you can have relations, other binary relations, unary relations, ternary relations, any sort of finite arity of relation. So you can have very rich structures like hypergraphs, where you're looking at not binary relations, but relations of higher arity. So this relational structure can be many things. But I'm going to call the domain the vertex set of it, just to keep it the analog with the graphs. And if you're looking at a formula phi, which is quantifier free, there's no for alls or exists in it. This is the only type of formula we're going to talk about, quantifier-free formulas. So we're given this quantifier-free formula, and we're actually interested in the structure I'm looking at, how many substitutions for the variables of phi give a satisfying assignment. So if phi is so phi, in fact I do have this example, but in the graph world, if phi is just this, then phi of the graph H is the so 5 either, well, it's up to swapping the variables, it's the edges. So the satisfying assignments are that.
So this formula is first order formula.
Yes, sorry, first order quantifier free.
Okay.
Yeah, first order quantifier free. That I didn't. Yeah, first order quantifier free.
What is the language? Just the equality and adjacent?
Yes, you assume the equality, and then the relations I haven't specified, but you're given some set of relations. So you can have adjacency if you want it, but you can have it's an arbitrary set of relations. So yes, the language includes equality plus something else. And I'm not saying what that something else because it's arbitrary at this stage. For a graph, you have this relation. Yeah. This symmetric binary relation. So for a graph, you just have this.
And then you can choose any axioms you want for the relation to satisfy.
Yes, it's just just any relate. Yeah, it doesn't matter how as long as you can decide whether something belongs to the relation or not. So if I look at this formula phi, which is the conjunction of these terms, Vi is adjacent to Vj, then the satisfying set for this formula in my graph H is precisely the set of substitutions that correspond to homomorphisms. So I and j are vertices in G. So if I'm sending a vertex of G to Vi, then this thing is saying that when I and j are adjacent in G, they must be adjacent in H. So this is precisely to say that it's a homomorphism from G to H. So this is a first order quantifier-free formula whose satisfaction set corresponds to counting homomorphisms. So I'm interested in the size of the satisfaction set. And it includes as a special case what I've been looking at. Right. And so I'm going to make a definition that a sequence of relational structures is strongly polynomial if for all the first order quantifier free formulas phi, there is some fixed polynomial r of phi such that the size of the satisfaction set is a polynomial. So it's just analogous to how we've defined it. And then there's this very useful lemma that this seems to be much stronger. I'm allowing any sort of quantifier free formula, but actually it's equivalent just to specify that homomorphism formula gives a polynomial. And this is because for quantifier free formulae, it's a sort of locality idea that the satisfaction of the formula only depends on a local sort of area of the domain. So it depends on the isomorphism type of the induced substructure. So the quantifier free is enabling us to make this equivalence. And this is actually a sort of key lemma to make this technique work that I'm describing. So another example of a non-graph sequence which is strongly polynomial is to take a transitive tournament is a acyclic orientation of the complete graph on k vertices. So this is a digraph. So it's not a symmetric binary relation. But so these are strongly polynomial sequences, and because of this, I can just say, oh well, it's obvious that what sort of induced substructures can I get? Well, I can only get subtournaments, and that's easy to count. It's just like for the complete graph, it's k choose j for subtournament of size j. So just by counting induced substructures, I can verify that it is strongly polynomial. So for every quantifier-free formula, the number of satisfying assignments for in the tournament of size k is some polynomial. And here's schematically what is Patrice's insight that is making things happen. So what we're looking at are what are called interpretation schemes. And we're looking at graphical interpretation schemes, which means that we go from some arbitrary relational structure. This sigma is the set of relations, so it's the signature of the relational structure. So for a graph, sigma is the binary relation. So for an arbitrary relational structure, this interpretation scheme sends it to a graph. So it sort of converts this structure into a graph in some way. And the some way involves that it only uses quantifier-free formulas to do it. And the lemma that makes things happen is that if I've got an interpretation scheme like this, then for every quantifier-free formula on graphs, in particular the one that expresses whether something's a homomorphism, I can send it to a formula in the language of this sigma structure, I tilde of phi, so that the satisfaction set in the graph, I of A, so I've gone from A to the graph H, so phi of H, the satisfaction set is precisely the satisfaction set of I tilde of phi in this richer structure. In particular, if I know that I've got a strongly polynomial sequence of relational structures and I interpret them, then I get a strongly polynomial sequence of graphs. And so this is where the sort of magic happens. And so all the previous constructions, complementation, line graph, and so on, are special cases of interpretations from graphs to graphs. So to do the complement, I essentially am using the negation of the formula. And any graph construction that can be expressed in a quantifier-free first-order formula. So you can get very complicated ways of combining graphs. And hooray, so this includes the Cartesian product. This is easily given by a quantifier-free formula. And other products too. I need to just make sure I don't run out of time. So that was the sort of the sort of nub of the technique. Go to richer structures and you can produce something more. And these generalized Johnson graphs you can also express in quantifier-free way as an interpretation of transitive tournaments. So you do need to go beyond graphs to get them. You go to digraphs. And then you get something which is quite interesting, because this sequence doesn't have this nice full sort of symmetric automorphism group that makes things work. And when we're working in graphs, we're basically depending on the automorphism group having a symmetric subgroup on K. And that was basically what was happening. And then you get these half graphs, which turn out to be you can build from a transitive tournament. And then you sort of have two marks telling you whether the vertex is an upper vertex or a lower vertex. So you have two unary relations and the transitive tournament, and then you can describe, using those relations, how to join the vertices together, namely join an upper vertex to a lower vertex if it's to the right. Yeah, so I join the upper to something immediately below or to the right, immediately below or to the right. And this you can express using this language of transitive tournament with the marks. And so you can build that graph using that structure. And you can do more sort of exotic things. You can make intersection graphs. This is also from a transitive tournament. Transitive tournaments seem to be the basic building block we're looking for. And conjecture, you can get everything from a disjoint union of transitive tournaments with some marks. That's certainly what we've found so far. There's a way of encoding a sort of an arbitrary relational structure using the transitive tournament. So you can sort of go to the transitive tournaments and then go to the graphs. So for an arbitrary relational structure, you take tuple, because you've got a linear order essentially on the transitive tournament. You can pick out what are your higher order relations. So there's a way of reducing things to the transitive tournament, but we're still not sure about whether these basic sequences are enough. transitive ornaments with some colours or marks. Right, well that actually went a bit quicker than I so hopefully some sense of the construction. It's sort of lifting from the worlds of graphs to these arbitrary relational structures, which you can think of being these tournaments with marks, and then using some way of building using that richer language, and then projecting back down into the graphs. And that's how we're building. And so we got the Cartesian product and the Johnson graphs, and we get many other things. Any sort of type graphs, if you know what those are, and very, very strangely defined graphs. You can do a lot using the... So actually I might have time to describe an interesting subproblem. Anyone in number theory in the audience? No, elementary number theory. It's nice, this. So if I take a prime pair that leaves remainder 1 when I divide by 4, then the non-zero squares in this field have the property that the negative of a square is also a square. And so we build an undirected graph called a Paley graph, which is the Cayley graph on the field of order Q, where you join two vertices if they differ by a quadratic residue, by a non-zero square. And these are well known to be quasi-random graphs, namely that everything occurs in a Paley graph as it should do in the random graph on the probability edge probability half. So if it sort of given a fixed graph f, it occurs the right number of times in the Paley graph. And interestingly, there is a recurrence similar to deletion contraction, which is related, if you know about it, to the Lovász-Szegedy theory of contractors in graph algebras, only if you know about it. But if you do, then this is related. And you use this recurrence relation, which can give a reduction formula for a series parallel graph. Actually, the key thing is that it's too degenerate. You have a vertex of degree 2. And you can use a recurrence in order to prove the fact that this is a polynomial in Q for series parallel graphs. For instance, if I count triangles, there are this many in them. Now, what about for the first non-series parallel, for K4? It gives something rather interesting. Namely, if let's just think about prime Q rather than prime power. It's just easier. So we know that the prime has a unique representation as a sum of two squares, an even one and the odd one. And these authors proved that the number of K4s in the Paley graph, that should probably say induced copies. So the number of induced copies of, so a number of K4s in the Paley graph is given by a certain polynomial in Q and this mysterious guy X. So for instance, and actually this thing, when Q equals 17, this thing is 0. So 17 is equal to 4 times 2 squared plus 1 squared, so this is X. And so this thing, there are no K4s in the, and this is well known for Ramsey theorists as being the unique sort of graph on 17 vertices which has not got the K4 or complement in it. And I think there are other Paley graphs for when you're looking at for no K6s, the Paley graph on the 101 vertices is the only known one not to contain the K6 or the complement. So this is an interesting and a couple more examples sort of leads me to hope that actually it's polynomial always in Q and X. but it's involving. I mean, you're working with Legendre symbols and things. If you're familiar with these guys, then you might be able to have a handle on that. But it'd be nice if that was true. As a side remark, there is a theorem that in this paper that we're currently writing. Actually, while I was preparing for this talk, every day I was getting updates on the paper from Patrice. So it really is in a sort of in progress sort of paper. If I have a strongly polynomial sequence, then it can't contain infinitely many Paley graphs. It can't contain infinitely many quasi-random graphs. Basically, because for a strongly polynomial sequence, the number of subgraphs you can find in them is quite sparse. You can't find everything. If you look at for a fixed graph f and you ask, does it occur in some of the terms of the sequence, the number of these graphs f is significantly smaller than for a random graph. And this is actually a special case of if you're familiar with these graph limits, this sequence of graphs converges to a random free graphon, if you're familiar with the Lovász theory. So some other open problems to finish. If you study Cayley graphs, we haven't really resolved this. We haven't really looked at it hard enough. But so the Paley graph was an example of a sequence of Cayley graphs. But I mean, there's a general question which has been answered in a special case for Cayley graphs on the cyclic group for a fixed sort of subset. This graph, by the way, so the vertex set is this group AK, and the edges are between two elements of AK when their difference lies in this set BK. So for the Paley graph, this was the field on Q elements, and this was the set of non-zero squares. Oh yes, I mentioned right at the beginning, remember, you only needed to look connected graphs. There's a good reason to believe that if I can check. Well, this is actually similar to this result for a random graph. So you only need to check that the edge and the cycle of length 4 occur the right number of times, and then it must be the random graph. Can I just check this for cycles or something, and then it's bound to be a polynomial? If G is a cycle, if I just take G's to be cycle and I check that it's a polynomial for all those graphs, then is it true for every graph? And there are some good reasons to think that there must be some restricted class, which I can't go into. And then, reduction. So we had these deletion contraction for the chromatic polynomial. We had that reduction for the independence polynomial where you deleted a vertex or you deleted its neighborhood. And these were reducing the size of the graph. These are size-reducing recurrences. And we don't actually have any other recurrences for these polynomials yet. But we haven't had a chance to look hard enough yet. But and then develop a similar theory for homomorphisms from a sequence to a graph, because if you're familiar with the characteristic polynomial, this sort of arises naturally in the and from my which I've now forgotten how to say, I've come to my yes, I've run out of breath too. So and these are the papers for